Hi, everybody. My name's Mark Phillips, and I'm going to talk about a project that has to do with rain. And I'll start by saying it is not my fault that it's raining today, but it's convenient because that's what I'm going to speak about. This is a project that started as a work-related project, but then grew into kind of a personal thing that I worked on off and on over the last year. And ended up writing a kind of a fun web visualization that combines some computer science algorithms and math and environmental science and hydrology. So let me just start by jumping into a description of what the main question is that this project was designed to address. And I can say it like this: given a spot on the ground indicated by, say, that yellow dot, when it rains there, where does the water go? So what's everything that's downstream from that particular location? And then there's kind of an inverse problem of what's everything that's upstream from that location. So what's the entire region within which all the rain that falls in that region is going to flow past that yellow dot? So my background is actually in math and data visualization. I'm not a hydrologist. I've spent a number of years working with climate and some environmental data. But I had to learn a lot about hydrology and hydrology data sources in order to start to answer this question, and ended up writing a web application to visualize what I found. And so I'm going to start by showing the application and then take a step back and take it apart and talk about the data that went into it and what it took to create it. So let me first flip over and just give a quick demo. So this is it. I'm running this locally, but it's online at that address if you want to check it out. So this is an interactive map of the United States. And what's happening is, as I move the cursor around, it's highlighting everything in blue that's downstream from where I'm pointing, and everything in red that's upstream. And I can zoom in on the map a little bit and say in a little more detail what's going on to make it make more sense. So this yellow region, this is all done in terms of these regions called watersheds. And whichever region is directly under the cursor, it highlights in yellow. And then all the ones that are upstream from there, it highlights in red, or maybe it shows up as kind of a brown there. And then everything that's downstream is in blue. And one thing that I immediately noticed when I started working on this that surprised me, but then once I thought about it, it made sense, is that there are a lot of points where there isn't much of an upstream area, like right there. There's no red. There's a lot of blue, of course, but no red. And then every now and then you get to a spot where there's a big red area. And at first when I started working on this, I thought something was wrong, but then I realized, no, that actually makes sense, because when it rains, water runs pretty quickly into creeks and streams and makes its way into rivers. And it's those rivers that have large upstream areas. A random spot on dry land doesn't typically have a very big upstream area, because if it did, it would have turned into a river by now. And so that's what gives rise to this kind of flashing effect as I'm moving the mouse around, is when it crosses over a river, it hits a place that has a big upstream area. Anyway, we can zoom out and look at some kind of interesting things here on a large scale. Notice that there's a place here, kind of an imaginary line, that as I move back and forth across it, the downstream drainage jumps from the Atlantic over to the Mississippi or the Gulf. That's the Eastern Continental Divide. And by definition, the Continental Divide is an imaginary line that divides the continent into two regions based on where the water flows. There's another continental divide out west, the Western Continental Divide, or sometimes it's just called the Continental Divide because it's bigger, that separates the Pacific drainage from the Gulf, or the Eastern drainage. Another thing that's kind of fun to do is to zoom in on downtown New Orleans, which is where, of course, the Mississippi empties out into the Gulf of Mexico. And I'm going to highlight the Mississippi River near downtown New Orleans, and then zoom out, and you can see the whole drainage area that drains to New Orleans. So if you were Huckleberry Finn, you could get on a raft, theoretically, anywhere in this red area and float all the way to New Orleans. Or since St. Louis is in the middle of that big area, you can see that New Orleans is where all this rain we're getting today is going, which is not surprising because we're right next to the Mississippi River. Some other cool things to look at here are to zoom in on Chicago, and I'm going to leave the Mississippi watershed highlighted. Notice how close that red watershed area gets to Lake Michigan. In fact, it actually overlaps Lake Michigan a little bit. And that's interesting. That didn't used to be the case. There's a river here that runs through or very near downtown Chicago called the Des Plaines River. And in the 1800s, some canals were put in to connect that river with Lake Michigan in order to allow ships to transfer from the Great Lakes to the Des Plaines River flows into the Illinois River, which eventually meets up with the Mississippi, I think right here near St. Louis. And so that's what gave rise to Chicago as an important transportation hub. So in some sense, you could say that this visualization helps explain why Chicago is the big city that we know it as today. Another thing that's kind of fun to look at is to follow starting from here in St. Louis, follow the Missouri River out west over into Montana, and to see where we can get to, somewhere right around here, I think, where you cross over the Continental Divide to the Columbia River drainage area. This is the route that Lewis and Clark took in their famous expedition in the early 1800s, where they were looking for the easiest way to get from the middle part of the country, in particular here in St. Louis, to the West Coast. And of course, in those days, traveling on water was the easiest way to go. Another kind of notable thing is look at what's going on here in large parts of Nevada and Utah, where the downstream drainage never makes it to an ocean. There are some rivers here, but they tend to just kind of peter out like that one. And like here's Salt Lake, and there's the region that drains into Salt Lake, but nothing drains out of it, which I think is why it's salt water. But this whole area here, with the property that there's no outlet, is called the Great Basin. It's called a basin because it has no outlet. It has the distinctive property that all the rain that falls there eventually evaporates. So anyway, you can play around with this and look at any other particular area that you're interested in and kind of get a rough idea of how the water flows. But let me take a step back now and talk a little bit about what went into creating this. Like I said, I'm not a hydrologist, but I had to learn a little bit about U.S. Geological Survey hydrology data in order to do this. And so I'm going to flip right now to a different visualization that I'm going to use to give sort of a conceptual explanation of how one might go about modeling the flow of water across the surface of the land in a computer. And what I'm going to explain right now is not what the visualization that I just showed is actually doing. This is just a conceptual explanation that explains the nature of the data, and then I'll talk about what the application actually does. But what I've got here is a virtual patch of land in a 3D program using WebGL and 3JS that I can turn around and look at from different angles. And the coloring is such that the lower elevations are green, the higher elevations are white, and the middle elevations are brown. I want to talk about how one might model the flow of water across this, and in order to do that, I'm going to zoom in on one particular point on the edge here and turn on a little blue ball that represents a virtual drop of water, and talk about how we might compute the path of that drop of water on its downstream trail across the land. And I'm going to speak in kind of an idealized situation here where I'm going to pretend that this land is completely non-porous, so no water soaks into it, which of course is not realistic, but it's a starting point for coming up with a way to model the situation. And also that there's no friction, so that the water just always moves naturally in whatever direction is most downhill. And let me zoom in a little bit more, and I'll turn on some edges in the graph, because the way this terrain is represented in the computer it's a collection of discrete points. So there are just data points at the intersections of these grid lines. And you can see that in more detail if I turn on down below a copy of just the XY grid, and let me raise it up a little bit and turn it so you can see that the location of all the grid points above correspond to the dots in the plane down below. So these are the XY coordinates of the data points in the terrain model. And so this drop, living on the surface, is going to move from one point to another. And so in its downhill journey across this land, let's say it's starting right here, and the next location it's going to be is going to be one of the neighbor grid points. And there are 8 of them, and I'll highlight them here. And I've highlighted one of them in green. That's the one that's most downhill. So that's the place where the drop is going to go next in the next time step. And we can see that even more explicitly if I'm going to zoom in on the grid points down below and temporarily turn on the labels, which I'm not sure if you can read that, but the blue point where the drop is right now is 982 feet above sea level. And it has 8 neighbors with these other elevations, and the lowest of which is the lower right, circled in green, and it's the one that says 873. So let me zoom back out now and move the drop one click so it goes there. And then I will move the neighbors to be relative to that new location. So then the next step, it's going to go to whatever the next lowest one is after that. And I'll do a couple more. And then it gets to the edge and it stops there because that's where the data ends. And so this kind of explains a way to model how the drop is moving across the surface of the land. And we can kind of see that more explicitly by zooming in down below. Let me just turn this a little bit. So what I explained was a rule that says that wherever the drop is, whichever grid point it's at, the next grid point it's going to be at is whichever neighbor is most downhill from there. And so that gives a rule that associates for every one of these points another point that's the next place it's going to go. And I can indicate that by turning on these arrows. So each dot has another dot that's one of its neighbors, which is the next place that the drop goes. Now you might be wondering, well, what if it's at a local minimum? What if all the neighbors are higher? And the answer is that that can happen in theory, but in practice, in the real world, it doesn't actually happen very often because local minima tend to get filled in with either water and become lakes, or filled in with sediment, and that raises the height of the ground, which changes the elevation, or the land gets eroded away. And so those kinds of situations are not stable and tend to be the exception rather than the rule. And overall, the flow of the water is always governed by this, kind of most downhill rule. And so for this particular example, I tweaked a couple of points in the data set to eliminate those kinds of situations. So this particular grid has the property that every point has one neighbor that's most downhill from it, except for a few that are along the edge. And so that turns this big grid into, you can think of it as a directed graph. The grid points are nodes in the graph, and these connections are like directed edges. And in fact, this is an acyclic graph. It's not hard to convince yourself that there are no cycles because remember, a path in this graph is a downhill trajectory, and you can't have a downhill trajectory that winds up back where it starts. So this is a directed acyclic graph, or a DAG, and this DAG pretty much exactly represents the way water will flow across this surface in terms of the computer model. And so that's great. We can use it to draw trajectories like this one little one that I've drawn right here. But there's an issue with this, and that is that the terrain grid is huge. Real-world elevation data has points about every 10 feet. And if you use a grid like that for, say, the entire United States, you end up with a grid with over 1 trillion data points in it, or a DAG with 1 trillion nodes. And that's just way bigger than you can do anything with on any kind of practical scale, certainly not in an interactive program in the browser. So we need a different way to represent the water flow that's more scalable. And there is a way to do that involves using this DAG to kind of analyze how the water flows locally. So let me turn the surface back on and turn the edges off so that we can see it. And I'm going to zoom out, and I'm going to use that DAG to compute several trajectories of water across the surface, or you can think of it as several possible streams. So I'm going to place a drop in those high mountains in the upper right corner, and let me change the radius of the drop to be ridiculously large so that everybody can see it. And then I'm going to tell the program to animate moving the drop according to the arrows in the DAG until it gets to the edge. And I think I can speed it up a little bit, yeah. So it comes down out of those high mountains in a valley in the upper right and comes into that central valley and then winds up in that point kind of along the front edge there. So let's do a few more just to get a general idea of water flow across this patch of land. So there's another one, and it meets up with the first trail or the first stream, and from that point on, they're the same. Let me do one over here on the left, and it goes off to a point on the left edge, and I'll do just a couple more at various places. Oops. And one more here. So a lot of these have the property that they meet up in that central stream or central river in that big valley. And they have in common the fact that they end at this point where the huge drop is right now. So that's a natural point to kind of focus on. So let me change the radius back to kind of normal. And I'm going to focus on that point and turn on the grid down below with the arrows. And so you can see the blue trail that I drew both up on the surface. Let me turn the edges off. So the blue trails up on the surface as well as in the grid down below. So all these trails, or several of these trails that I drew, end at this point on the edge right there. So a natural question to ask is, what are all the trails that end at that point? So let me highlight that point in yellow and get rid of the surface up above. And so the question, what are all the trails that end at that point, can be answered by using this DAG by following the arrows in the reverse direction. Or another way to think about it is just reverse the direction of the arrows, and you get a new inverse DAG. And so the collection of all points that are reachable from the one that's highlighted in this inverse DAG is the collection of all areas that are upstream from this location. And that's something that's easy to compute with a DAG. You just use depth first or breadth first traversal or search. So I'm going to tell the program to do that right now, and it's going to highlight in red. It takes a couple seconds to render everything that's upstream from that location. And before I forget, let me turn the arrows back to point in the downstream direction. And then I can zoom out, and we can see that what this does is it defines a big polygon. And try to center it a little bit. Yeah, so there's a big polygon that is the whole region that's upstream from that one selected point. And we can also take a look at that up on the surface up above. And sort of unsurprisingly, that polygon corresponds to the big central valley on the terrain. So that's the region that's upstream from this one location. Another way to think about this polygon, if you go back to the DAG, is that it's, if you think of the DAG as just a undirected graph, this is the connected component of this yellow point here. So if you divide the graph into connected components, or in terms of the directed graph, the weakly connected components, it provides kind of a natural way of grouping areas of the terrain into regions that sort of share water flow properties. And so this one big polygon is sort of the largest component in the terrain patch that I have, but you could imagine doing this for a much larger patch and have several big connected components like this. And the amount of space that it takes to store this polygon, just all the points along the edge, is tiny compared to the amount of space it takes to store the entire grid. So this polygon, together with the information about where its outlet point is is a much more effective way to represent something about the water flow. And if you want more detailed representation of the flow, you can use the same algorithm to divide the polygon by picking another point in its interior somewhere and doing the upstream computation from there. So let me switch back to the terrain, and you can subdivide anywhere, but a natural place to do that is near places where streams come together. So I'm going to focus on this place right here, kind of halfway up the Central Valley, and put a little yellow dot there at a spot that I'm going to run the upstream traversal from relative to that location, and then zoom out so that we can see it. So that divides the original polygon into two, or the original valley into kind of two smaller valleys. You can see the edges of the division kind of follow the local ridges in the middle there. And we could subdivide again by focusing on another point. Let me say, go into just above this place where the streams come together right here. And I'll do the subdivision one more time. It takes just a couple seconds for the graphics to render. And so now we've subdivided the original polygon into three pieces. And I'll zoom out and go back to the two-dimensional view. And at this point, let me turn off the blue streams so that we can clearly see the edges of the polygons. So what we've got now is a situation where there's three polygons, and all the water from the top one drains into the second one at that one point, and all the water from the middle one drains into the bottom one at that one point, and the bottom one drains out at the point indicated at the bottom of the screen there, and no water crosses an edge of these polygons except at those points. This is how watersheds are defined. It's a hierarchical collection of polygons, and this is exactly what hydrologists have done. Now in practice, I don't think they do it by defining DAGs and doing it completely computationally like this. I think in practice it's a complicated process of surveying and understanding river flow and taking into account in some cases flow of water under the ground and so on. But conceptually, this is what's going on. And so you can download a data set from the US Geological Survey called the Watershed Boundary Dataset that contains the borders of these polygons and the flow relationships between them. So when I realized that this data was available and that that's what it means, I thought, oh, cool, I can use this to write a little web application like the one that I showed. And so I downloaded the data and plotted it, and this is what it looks like. This is the outermost, the two top levels, the big thick lines are the edges of the top level, and then the second level is the thinner edges. And this data set has 6 nested levels of polygons. And so I'm going to zoom in to this one particular area over on the East Coast and turn on the successive finer levels until we get all the way into the most detailed one, and highlight this one particular polygon right here. And so this polygon has the property that there are 2 other ones that flow into it, this red one and that red one, and they flow in at the places indicated by those arrows. And the yellow polygon flows into the one in the upper right that just turned blue at that spot, and that blue one flows into this other one, and that flows into this other one, and so on. And we could follow this all the way to the coast, but I'll just stop at this point and point out that this relationship between these polygons, the fact that each polygon has one other one that's downstream from it, is really similar to the relationship between the grid points in the original DAG. So you can think of these polygons as nodes in a graph, and the flow relationship between them as directed edges. And so we get another DAG that describes the flow of the water across the land. But this DAG is much, much smaller than the original one. The original one would have over 1 trillion nodes, and this data set of polygons has about 100,000 polygons. They're about 5 or 10 miles across, roughly. And that's a big number, but it's small by computer standards. You can loop over 100,000 things really quickly in a program, even in a web browser. So I downloaded the data and started trying to write an interactive program to display it, but I ran into a couple challenges. The first of which is that the data set takes up 6 gigabytes. And so when I looked in more detail at why that's the case, like say looking at one particular polygon, one reason is that the edges of the polygons are defined by hundreds, if not thousands, of vertices, which is way more detailed than I really needed for my application. But that's okay. There's a lot of good open source GIS software that will simplify polygons by dropping out vertices that don't contribute very much to the shape. So you can run this polygon through a simplification program and replace it with another one, like say this green one, that has just a few dozen vertices. And it, when you zoom out to most scales, it pretty much looks the same as the way it started. But then there's another issue, and that is that, remember, there's 100,000 of these polygons, and they're all right next to each other. They share edges. And in the original data set, it's in a format where the polygons are stored individually. And so these shared edges are stored twice. And the edges may match up exactly, but the data's in there twice. And so when you run the simplification algorithm on each polygon separately, what happens is that it sometimes simplifies that edge differently for each polygon. And so you end up with mismatches. So little gaps like here, or overlaps like that. And that turns out to make way more difference than I would have thought in kind of the visual result when you use this to draw pictures. So I needed a way to resolve that. And the solution was to convert the data to a format that doesn't store the shared edges twice. It stores the shared edges only once. And there is a format, there's several, but the one that I used is called TopoJSON, which is another good thing for my interest in writing a web application, because it's kind of optimized for web use. And so by converting the data to TopoJSON and doing a simplification algorithm using the TopoJSON format, I got a good clean data set with matching edges and got the size of the data down to about 50 megabytes. And so that was much more workable in terms of something I could do in a web application. So I set about making an interactive map using Leaflet.js, which is Leaflet's a great JavaScript mapping library. But it turns out that Leaflet uses SVG for rendering polygons by default. And this picture right here is showing the Mississippi watershed for New Orleans. And this has about 40,000 polygons in it. And SVG is a DOM-based rendering API. And so what that means is that each polygon ends up being a node in the DOM. And if you've done much DOM programming, you know that DOM manipulation is notoriously slow. And so the first time I did this, the browser just ground to a halt and I think even crashed with 40,000 nodes in the DOM. But it turns out that Leaflet also can use the HTML5 Canvas API for rendering. You have to install a plugin, but that's fairly straightforward. And so by doing some custom HTML5 Canvas rendering code, I switched the polygon layer to using that and got the rendering time down to 3 or 4 seconds for this large collection here. And in situations where the number of polygons was much smaller, it was really fast. And so that was fairly somewhat usable, but I wanted to make it even faster. And so I did one more optimization. And that came from noticing that when it's drawing a large red upstream area like this, that actually consists of a whole bunch of individual polygons. And they're all drawn individually here, so you can see the edges between them. But all I really cared about was drawing the whole big red blob. And one of the things about computer graphics is that the amount of time that it takes to draw something typically depends on the number of vertices involved. And so by pre-processing these upstream areas and removing those interior edges, it reduced the number of vertices significantly. And so it got the rendering time for these large blobs down from, say, order of n, where n is the number of polygons, to roughly order of square root of n. And so for large values of n, that was a huge improvement. And so that's what finally got the rendering time down to several frames a second and allows the program to be fairly responsive. So let's see. One other thing is that there's a mobile version. And for the mobile version, there's a couple things that are different. One is, of course, there's no mouse. So there's no cursor, no hovering. Typically, interaction with a mobile application is through tapping. And then also in a mobile device, you typically don't have as much memory and often lower bandwidth. And so the way the mobile version works is that it's a map using leaflet, and you can pan and zoom around, and then you tap, and the mobile device sends the latitude and longitude of the place where you tap to a service. And the service responds with the ID of the watershed that you tapped on. These watersheds are called HUCs. It stands for Hydrologic Unit Code, is the technical term for the ID. And then the application makes another request to a CDN for a little topo.json file that contains just the geometry of the upstream and downstream region for that particular watershed, and the application then renders just that. So that allows the mobile app to respond fairly quickly. So that's pretty much it. That's how the program works. Let me end by going back to the program and zoom in here on St. Louis, because we're at a particularly interesting place here in St. Louis with regard to rivers, of course. So here's downtown St. Louis. This is down here in the, well, here, let me mouse over there. And then, so down here is the Mississippi, and then this is the Missouri River coming in from the west, and the one that's kind of straight up and down here is, I think, the Illinois River, and then the one in the middle is the Mississippi coming down from Minnesota. And so by changing the base point here, I can highlight just the Missouri part of the watershed, or just the Mississippi part, or just the Illinois part, or by coming down here on the Mississippi, can highlight the whole collection of all three of them. So there's the whole big area that eventually drains here to Mississippi, or excuse me, to St. Louis along the Mississippi. So that's it. There's my contact information, and I think we've got time for a few questions. There is, and this program doesn't use that, but there's like average flow, per year or per month or whatever. I don't remember exactly the detail of what's there. And then, of course, there's also live data that's a completely separate data set where you can go and find out what's the amount that's flowing past, there's something like 20 or 30,000 river gauges around the country that you can go get live data from. I think so. I mean, you'd have to implement something kind of on a grid-based scale, like the sort of conceptual explanation that I used. But absolutely, yeah.
So in Pennsylvania, we have a lot of floods, and as a mission pilot, I take a lot of photographs of flooded areas, and they go to FEMA, and I can see the next thing people are going to want to know. They're going to say, "Oh, this is so awesome! Now knowing if we know this much rain is going to fall in the next few hours, who's going to flood?" Because I know we've had at least 200 or 500-year floods in the last few years, and everyone wants to know, because it affects insurance, who gets covered by flood insurance and who doesn't. That's what people on the ground want to know. I can see an application for this like immediately. All kinds of people excited about it.
Yeah, yeah. I mean, there's obviously big parts of the government, parts of the Weather Service that, focus on river forecasts, and they use this data all the time.
They don't have this dynamic visualization that you've created. Everything, I haven't seen anything like this.
Yeah, it's fun.
But it's useful.
Yeah, yeah. I imagine the people that work with this all the time sort of can visualize this in their heads. But yeah.
What software or library were you using when you were showing the topographical map and the 3D grid needed?
The topographical map with the water trail? Yeah. Yeah, that was a program that I wrote using Three.js, which is a WebGL library. Okay. It's just a custom program that I made for making this presentation. It's actually that second URL there. It's on GitHub if you're interested in taking a look. But it's not particularly set up to be usable for anything other than my talk here.
Yeah, just kind of building on the things you were talking about of, as you say, there's all these government agencies that try and predict where floods will happen. And I was wondering if you know this yourself or have talked to people who study hydrology about, like, so I feel like a lot of things that I've heard for why that the government agencies need to make very accurate predictions on where the water's going to go. And it seems like a lot of times in interviews they say that they prefer to rely on physical models rather than computational ones.
Mm-hmm.
Because they don't get that level of accuracy from the computational models. And I was wondering if you have any idea about like how accurate your model is here, and do you have any goals to make it more accurate, like to incorporate things like groundwater?
Yeah, so I don't have, so the question has to do with how accurate is this model and kind of the balance between computational models versus physical models. And like I said, I'm not originally a hydrologist. I just got this data, understood what it is, and wrote the program. I think that a lot of effort went into defining these watersheds that takes into account a lot of physical properties. I don't think that these watersheds were computed computationally. There may have been some computational kind of assistance along the way, but I think for the most part, it's a long and ongoing process of manual surveying, and they're constantly putting out new versions of this data with new information.
Have you done any work modeling forest systems and caves?
Forest systems?
Forests. Or we mentioned that caves have like friction or porous ground, there is no model, so I wondered if you implemented that.
I'm sorry, I'm still not hearing quite the word. Modeling what?
Modeling forests.
I have not. Forest, no.
Forest. Was it forest?
Porous, oh.
Right? Yeah.
I have not. Short, easy answer, no. It would be interesting and way more complicated.
In the western United States, I know water rights are determined by who is upstream, I think, or being upstream has some kind of advantage. Does anyone use this visualization to investigate that, or maybe even like settle legal claims to water sources?
I hope nobody's used what I've done in any sort of legal way. But all I did was take the USGS data and display it. I'm sure the data itself has been used in lots of ways, and that's the point of why the U.S. Geological Survey creates the data. Any other questions?
Have you considered visualizing this by not highlighting a single polygon, but coloring all of them once by how many other polygons depend on this one, like in a gradient?
Ah, that's interesting. No, I haven't, but that's a great idea.
On first thought, it would be similar to like just what you showed initially with this 3D map.
Mhm.
The bottoms are green and sides are white.
Right.
It should not depend on how high it is, but how many other polygons.
How many other things are upstream? Right. So the darkest areas would be the rivers, and the lightest ones would be the peaks, but in a way that's not just elevation. It depends on the whole topology of connections there, yeah.
Is this thing open source, right?
Yes, yeah, the application is online there, and the code is on GitHub, yeah.
Time. Maybe
Yeah,
one
yeah.
more
Yeah.
question.
If there's another question, I can take it. Otherwise, I'm happy to hang out in the hall and continue chatting, yeah.
Quick question. So you talked about this optimization where you got rid of all the interior edges of your polygon.
Right.
But I just wanted to clarify, the thing is there's a trade-off there because you didn't do, I mean, the individual polygons still exist in the sense that when you mouse over them, they're still there.
That's right.
And so it seems like you're essentially going to have more data then because you're going to have to, for every individual polygon, you're going to have to pre-identify this region
Mhm.
upstream and downstream.
Yeah. That's a really good point. So I had to pre-process the data, and it did increase the size of the data that gets downloaded a little bit, but not very much, because all the vertices I had to download the edges of the individual polygons anyway, and all the edges of the aggregated blobs are already included in what was there. So it's an extra set of references to those edges. So it added like 1 megabyte to the 50 megabyte file or something like that. Well, thanks again. I'm happy to continue to hang out and chat.